Let's now examine DTFT when the input signal given to us, xn, is not periodic. What it also means is that capital N, the period, goes to infinity. If we look back at the DTFS equation where the sample was n periodic, then when the big N goes to infinity, 2 pi over n actually goes to very, very small. And you will realize that k times a very, very small value will tend towards the real range. So this is what's happening over here, where we are no more dealing with discrete frequency. Now this frequency becomes the real value. So let's see the equation for the analysis and the synthesis. So in this particular example, you realize that in the DTFS was 2 pi over big N times k. But now when big N goes to infinity, then it will tends towards the real value omega. So omega actually is very much the same as ck, but now we are actually examining for all omega, actually from 0 to 2 pi, or from minus pi to pi if you prefer, and in fact you will realize that x of omega is periodic by 2 pi. So let's see the frequency representation of xn graphically, which is here. The input signal is not periodic, it doesn't repeat. You will use x omega to get the discrete time Fourier transform of this aperiodic signal. You have to plug in all omega, every real values, there was infinite of them, either from minus pi to pi or from 0 to 2 pi. Doesn't matter because actually it is 2 pi periodic. So you realize that from 2 pi to pi is the same as from 0 to minus pi. So whether you're plotting from minus pi to pi or 0 to 2 pi, they all result in the same value. If this doesn't make sense to you, yes, it doesn't, because if it is really xn is aperiodic and it stretches to infinity, then you can't even compute this equation anyway. So this is very strange. But of course, if the number of non-zero value is finite, so the support is finite, then actually you can then correct it. So I'll give you the simplest example. Maybe you have only this value 0, 1, 2, and then minus 1, and then all 0 all the way. And this xn is aperiodic, right? Because it doesn't repeat. The only interesting thing is that these 4 values here, you can plug into this equation, and then of course then you can plug in different omega, and then you can sketch the discrete time Fourier transform of this sequence. Primarily because you could write some MATLAB code or Python code to perform this summation of xn multiplied by e minus j omega n. Then you'll be thinking, but you will need all omega. And of course you don't. Typically you look at this from 0 to 2 pi and you only divide it into maybe 100 parts or 1000 parts, up to you. Okay, and then you still can interpolate between these values, and that's what we do all the time. Because if I ask you to plot sine 2t and then this is t, and then you realize that you're actually plotting only, you have to plot for all t, but actually you are only interpolating, or you're only plotting some intermediate values, and you're not plotting all possible omega. Now, if you have gotten this far and you have gotten the frequency representation x omega, you'll realize that x omega is a continuous function. To get back to our xn by the synthesis equation, then we have to perform integration, because x omega is a continuous function with respect to omega. So it's integral from, in this case, I'm doing from minus pi to pi, but you can do it from 0 to 2 pi. It's totally the same. Then you can get this the equation, and you start to integrate, and then you will get xn. Okay, so this is the analysis and the synthesis equation for aperiodic sigma. And this is the graphical representation of the xn, which is aperiodic in nature, but the x omega is periodic in nature with 2 pi. Not only periodic, it is actually continuous. Thank you.